Hello and welcome. My name is Noah Deer, and today we're doing Lesson 6 for 4th term calculus at PCC, functions of several variables. We are going to look at the following topics: domains and graphing using GeoGebra. So if I have a function of multiple variables, then what does a graph look like? How do I find the domain of this function? We'll also look at things like the range of the function as well. We then also are going to look at level curves and contour maps. So if we have a top view of a function in two variables, then can we look at contour maps like a topographical map that shows what the elevations are at different locations on that map. We can also do this for three variables. Skip a topic here real quick, but in three variables we'll have contour surfaces, level surfaces, and talk about how that's analogous in that situation. And then we are also looking at graphing a function in two variables by hand. So for different kinds of functions in two variables, can we have techniques and ways of drawing what that graph looks by hand without technology? All right, so let's just hop right to it. So the general definition for a function in two variables is a real valued function f, for example, in two variables is a function whose domain is a subset of R2, that is a subset of the set of x comma y, such that x is in the real numbers and y is in the real numbers, and whose codomain is the set of all real numbers, or whose outputs are all real numbers. You can pause for a second and read this in detail if you'd like. In essence, what we want to realize is if we have the xy plane here and we pick a point in the xy plane, so here's x comma y, then as we plug this into our function, it's going to output some z value, has some elevation for this specific xy value in the xy plane. For this xy value over here, maybe it outputs an elevation down here with this z value. So here we have a point xy as our input and z is our output. So we can think of this if we're looking down from above, then this is our 2D map of some region, and for every point we have an elevation for that point, so we can create topographical maps, and we'll do that here in just a little while. So let's look at some specific examples. Graphing a real value function in two variables in GeoGebra is very simple. Open GeoGebra 3D graphing and simply type in the function and hit enter. So we're going to do that for this example after we find the domain of the function. So determine the domain of the function f of x comma y equals the square root of x squared plus y squared minus 16, and then use GeoGebra to graph the function. So for this function, because of the square root, we need the inside of the square root, the radicand here, to be greater than or equal to 0. So we look at the function, we say, what's my requirement for this function so that the inputs will give us an output? And we know that the square root function needs positive or 0 inputs. So we take the inside of the square root and we set it greater than or equal to 0. We can look at this as x squared plus y squared is greater than or equal to 16. A nice way of thinking of this is that r squared is greater than or equal to 16, or that 0 is less than or equal to r is less than or equal to 4. We could also write negative 4 is less than or equal to r is less than or equal to 4. But if we look at a two-dimensional graph of this domain, thinking of the radiuses as going from 0 to 4 or from negative 4 to 4 is going to give us the same picture. So both could be considered correct answers in this case. Because of the radius being less than or equal to 4, then we can have a solid line as we draw the domain. For the edge, if this was r is strictly less than 4, we would use a dotted line here to indicate that the radiuses can't actually equal 4. And so this is a graph of the domain of this function. If we want to graph this using GeoGebra, then go ahead and take a second, open up GeoGebra. I've already got it pulled up here. And all we need to do is type in the function. So I'm going to write f of x comma y equals the square root. Nice little abbreviation there, allows me to just get that square root symbol. You can also pull up the keyboard. Move this up. See the little keyboard symbol here and get our square root symbol here. But just typing SQRT is a nice way of getting that pulled up. So I have x squared plus y squared. And GeoGebra is really cool in that it pulls up these graphs as you're typing them, so you can kind of see what these different operations for the function are doing to what the graph looks like. Close this again. All right, so f of xy equals this, and we get this picture. Which tells me right away I made a mistake in my domain. So let's go back and look at that in just one second. And it's nice to be able to zoom out here. If I hold the shift key, I can kind of move the field around so I can see what this is looking like. But it looks like a funnel type of shape, right? And we actually see that the domain is everything other than that, which tells me that I got my inequalities wrong. So let's just use this as a quick opportunity to recognize we all make mistakes. That's okay. We just need to recognize when we make them and go ahead and go back and make the adjustments as necessary. So if I go back to my worksheet here, I see that r squared is greater than or equal to 16. R squared is greater than or equal to 16 should give me something that is outside of 4 and negative 4. So hopefully some of you caught that as you were watching the video earlier. And you're like, Noah, what are you doing? It's the other way. And you were absolutely right. So negative 4 is less than or equal to r, or r is greater than or equal to 4. And we can think of that here. So if r squared is greater than or equal to 16, then r needs to be like negative 4, negative 5, negative 5.5, anything less than or equal to negative 4, or r has to be greater than or equal to 4. So 4, 5, 6, 6.2, anything bigger than 4 squared will be bigger than or equal to 16. So as I graph that domain, it gets us outside of the circle. We still get this solid line here. And so here is a picture of that domain. And you can also click on this link if you want to see how I had that typed in. Hopefully you've got it figured out on your own, but it's always there for you. All right, so that is the example that I'm giving, and you guys go ahead and try this exercise. I will go through and talk through the solution here in just a few seconds. Go ahead and pause the video and give that a shot. All right, so if we're looking at exercise 6.1.1, determine the domain of the function g of x comma y equals the natural log of x times y, and then use GeoGebra to graph the function. So with the natural log function, we need the input, in this case x times y, to be greater than 0. So I write that down, and to think about this graphically is actually really nice. If I draw my xy plane, then I recognize when x and y are both positive, then their product will be positive. When they are both negative, their product will be negative. And we want it to be strictly greater than 0, so if x or y is 0, that's not going to work for us, because that would give us x times y equals 0. So I'm using a dotted line here and to indicate that the x and y axes are excluded from our domain. So here's a picture here. If I write this out in some detail, I can say x is greater than 0 and y is greater than 0, or x is less than 0 and y is less than 0. It's kind of nice to have parentheses around these so that we can see how we have two clauses with an and between them, and then a or separating two more major clauses of x is greater than 0 and y is greater than 0, all in parentheses, or in parentheses x is less than 0 and y is less than 0. The formal set notation here, we could write this in some more detail, but the domain of G equals a set of x comma y such that x times y is greater than 0. If we wanted to be more descriptive, we could write the set of x comma y such that, in parentheses, x is greater than 0 and y is greater than 0, close parentheses, or x is less than 0 and y is less than 0. Both of these are correct answers. The second one is giving us some more detail. I did go back, and in the previous problem I wrote the formal set notation here. The domain of f equals the set of x comma y such that x squared plus y squared is greater than or equal to 16. I left it in this form because we have our domain in terms of x comma y, so I'm leaving the x and the y in my condition for what our domain is, rather than putting in the r. Even though the r is nice and descriptive and helps us graph what this domain looks like, it's nice to leave the formal set notation in terms of x and y, since x comma y as a point is the domain, that our domain has to be in the set of x comma y, so we're just leaving it in terms of that. Okay, if we want to look at the function here, I've already got this graphed. G of x comma y equals the natural log of x times y. And get a top view here. Here we see the positive x and y areas, the negative x and y areas give us these graphs, and it gives us this actually like kind of a natural log shape thing when we look at it from the side in both directions. So that's pretty cool, and that is what that function looks like. All right, let's go ahead and move on. And please remember, you're welcome to pause and think through any of this, really process what I'm saying. I am going to go ahead and continue on and bust through this lecture here. So the next thing we want to look at is level curves and contour maps. So how can we look at a top view of the domain of the xy plane and see all of the different possible outputs? So if I look at this definition, definition 6.2.1, it says the level curves of a real valued function f in two variables are the two-dimensional curves in the xy plane with equation f of xy equals k, where k is a constant real number in the range of f. So we're saying since k is an output of f in the above definition, a level curve plots all coordinate locations that has a given z-value elevation of the landscape. Definition 6.2.2. A contour map of a real valued function f in two variables is a graph of several level curves of the function. So hopefully the idea here is that if we graph enough level curves of a given function, then we get an idea of what the three-dimensional picture looks like. We see a bunch of different z-value lines. So for given z-values, we can see where the function takes on that z-value and can hopefully infer in our minds what the 3D picture looks like from these contour maps. So let's look at example 6.2.1. A contour map for a function f is shown in figure 6.2.1 below. Use it to estimate the values of f of 1, 2 and f of 2, -5. So f of 1, 2 and f of 2, -5. We just want to say what are the z-values here. This is just a quick practice at reading these contour maps. So the contour map is already given here. I'm going to zoom in. We want f of 1, 2 first. So if I go to, notice the scale here is by 2, 4, 6, 8 in the x-axis and 2, 4, 6, 8 in the y direction as well. So if I go to 1, 2, we are about here. So the green circle here has a z-value of -1.45. The blue circle has one of -1. The green circle is that of negative 0.5, so we should be going somewhere between negative 1 and negative 0.5 for our z value. Since we're closer to negative 1, we can guesstimate that f of 1 comma 2 is probably about negative 0.9. And that's just assuming that this has a nice smooth output from negative 0.5 to negative 1. Now we could be totally wrong. It could jump up to 3 right here, but we're just going to assume that these circles are giving us enough information that it's a nice smooth going up from negative 1 to negative 0.5 between the blue circle and the green circle. If we look for f of 2 comma negative 5, I'll zoom back in here again, 2 negative 5. So 2 negative 5 is right here. This looks like we're right on the circle, so f of 2 comma negative 5 should be equal to 0.5. I'm going to change this equal sign to an approximation. We were definitely approximating here. So f of 1 comma 2 is approximately negative 0.9. F of 2 comma negative 5 equals 0.5, since it looks like we were right on that gray circle there. So I've got a few quick directions for how we're going to do this in GeoGebra, which I'm going to go through in a lot more detail as we actually do the example here, example 6.2.2. So let's start by opening up GeoGebra. I still have this open. I'm just going to start a new graph here. And in doing this, I'm just going to start by getting the 3D graph going. We'll just look at that. F of x comma y equals x times y to the third minus y times x to the third. And this looks like nothing is going on here. I have a couple of different guesses as to what's going on. I believe that my z-scale is way off, so I'm going to expand it up and see if anything happens here. Not seeing a change here. I'm wondering if I have those as multiplication. Oh, I know. I did x times y cubed instead of y times x cubed. Y times x to the third. And that looks much more interesting. Okay, so let's go ahead and scale this back down. There we go. Now we get a picture that looks more like what I had on the lecture notes. So this is a pretty cool function we have. This is better than a hyperbolic paraboloid. This is a hyperbolic paraboloid style shape, except for it's got, instead of just the down in 2 directions and up in 2 directions, we have up in 4 directions and down in 4 directions. But this is definitely a saddle point right here. It's just an even more complicated saddle point than maybe we've seen in other situations. So if we want to do our contour graph, I'm going to go ahead and open up a new, just basic graphing calculator in GeoGebra. I just type on my keyboard, so I want to close that. Remember, we have the function is x times y to the third minus y times x to the third. So we want to get different contours. We can start by just setting when is the z value equal to 0. And we see that we get these green lines. So all of these green lines are when we have an output of 0. I want to go ahead and here, settings, show label. I'm going to give it a caption of z equals 0. right there, we've got that caption. All right, I want to take the same thing and just look at different, when are the z values 1 or -1? So x times y to the third minus y times x to the third equals 1. And we get these blue lines. I'm going to do the same thing, give it a caption of z equals 1. Show label caption. And so we've got that there. And I'm just going to keep doing this. X times y to the third. I'm going to copy and paste this here in a second. X to the third. Y times x to the third. Oops. Copy that so I can paste it. Just put it on my clipboard. This equals, say, -1. And this is cool. We see the symmetry that we get the +1 in this top right quadrant and then the -1 in the top right quadrant also, but in the less than 45 degrees section, while the +1 is in the above 45 degrees section. We see that repeated in all 4 quadrants. So let's paste that again. Let's do, say, 8. Paste it again and say equals -8. Let's do some captions for these. This one, z equals -1. This one, z equals -8. Oh, I think I grabbed the wrong one here. So I wish I could move these captions to better locations, but it's not really letting me. It's okay, we're not going to do really anything else with this. So z equals 8. Is the purple line. So they do have the color matching, so hopefully we can use that to identify which ones are which. And now we can see, oops, do not want to move that. Come on, undo. Okay, so the edit undo ability is not as nice as I would like it, but I went ahead and just retyped that real quick and got this back up. So we can see that we have a elevation of 0 at the green lines, an elevation of 1 at the blue lines, -1 at the red lines, an elevation of 8 at the purple lines, and -8 at the gray lines. We see the elevations going up in this direction. So in, say, quadrant 4, in the less than -45 degrees, between the -45 degree line and the y-axis, we have elevations that are going down from 0 to -1 to -8. If we're looking between the -45 degree line and the x-axis, we have elevations that are going from 0 to 1 to +8, and we get like these almost parabolic, hyperbolic shapes here, except for they are split into 8 sections through the xy plane instead of into 4 sections. So pretty cool graph. And again, look at this and compare with the 3D picture, and we can kind of see, hopefully see what's going on, how that contour map matches up with this 3-dimensional image. Okay, so let's see. That's how we would do that in GeoGebra. And now we want to do this by hand, and we're going to start this in 2 dimensions. Just to give us a heads up of where we're going with this, we're then going to do this in 3 dimensions to be able to look at contour maps and use those to come up with the 3-dimensional graph. And then finally we're going to look at level surfaces. So if I have a function of 3 variables, how do we try and picture what that function looks like. Okay, so example 6.2.3, draw a contour map of the function f of x comma y equals x cubed minus y, showing several level curves. So I'll start by saying, when is this function going to equal 0? It's always nice to start there. So x cubed minus y equals 0. If I reorganize this as y equals x cubed, then if I know what this graph looks like, which I'm really hoping everyone here does at this point, then we can go ahead and draw this curve and see that that's where my z values are going to be 0. Let's look at a scale of by 2's here. So 1, comma 1 is that point, and then 2, comma 8, negative 1, negative 1, negative 2, negative 8. Let's move this. Now this should come and be nice and flat at the origin. We should, this is not the prettiest. I'm going to redo this real quick with pop. Alright, that's a little bit better. So here we have z equals 0. Then I'm going to change colors. Let's look at what happens if we set z equal to 1. So if x cubed minus y equals 1, then if we rearrange, we get y equals x cubed minus 1. Take a second, make sure you see where that's coming from. But if I add the y to this side, then subtract the 1 from this side, we should get this. So this is going to give me the same graph, but shifted down by 1 unit. So this is going to be really hard to distinguish from the previous level curve. They're just really close together in most locations. Here we get z equals 1. By symmetry, we should get that when z equals 1, we go up the other direction. Let's double check and make sure that I'm not wrong in that assumption. So if z equals negative 1, we have x cubed minus y equals negative 1. If we add the y to this side, add the 1 back over to this side, we should get y equals x cubed plus 1. So yes, indeed, we should get this point, and this goes up 1, this point goes up 1, and this point goes up 1. So I'm just using transformations of my y equals x cubed graph. So we see that it looks like all that's happening is that we change my z value, that this graph moves up and down. It gives me an idea of what this is going to look like in 3 dimensions. If I wanted to tilt this xy plane backwards, we see that we get like this cubic shape that's kind of shifting infinitely, where it's really negative the more positive y direction we go, and more positive the more negative y direction we go. Let's put in a couple more values here. Let's say when z equals 8. And why am I choosing z equals 8? I almost did z equals 5. I thought I'd do something a little bit bigger, kind of matching these values over here. It seems like when we had a 1 or a negative 1 for z, that just shifted it up 1 or negative 1 unit. So if I choose z equals 8, then maybe it will give me a bit more drastic of a shift. So if z equals 8, I get y equals x cubed minus 8. Sure enough. So we get all the way down here. Not even going to see the bottom half of the graph. Let's do z equals 4. Oh, already used orange. What else do we want to use? Do pink. Haven't used pink. Z equals 4. Let's do z equals -4. X cubed minus y equals -4. So y equals x cubed plus 4. Shifts it up 4. The blue line up 4. I promise I'm a better artist than this when I am not on a Wacom tablet. I'm not doing my drawing on Wacom tablets generally. So here we have z equals -4. So hopefully from this we can kind of see what I was saying earlier, that this cubic shape will see that same elevation being a cubic shape, but as we move in the y direction, in the positive direction, that shape moves downward. In the z direction, it moves upward. Let's, I don't have this in the lecture notes, but there's no harm in us taking a look in GeoGebra and just confirming what I'm saying here. So we have f of x, y equals x to the third minus y. So if we're looking from above, we see here's that z value of 0, right? This cubic shape, right, has 0, 0, -1, -1, negative, if I zoom out, we should get to -2, -8, and +2, +8. And if we go, say I do z equals, pause that, say, right, the plane z equals 1. So this is going to, if I look at this from the top, then we can see this line here, that is that y equals x cubed minus 1 shape. So we have -2, -9, 0, -1, 1, 0, and 2, 7 for our points on our cubic shape. So that does in fact happen. And it's kind of cool to see it from the side. We see also a cubic shape. We're not going to do the cross sections in all 3 dimensions today, but we can see if we turn this on the side that that cubic shape keeps shifting in a lot of different ways here. So if you want to, you're welcome to look at cross sections in different ways. And if you look back at previous chapters, specifically from chapter 9, you can see some examples of how to do cross sections where instead of just keeping the z value constant, we can keep the x value constant, the y value constant, and see those shapes in all those different directions. Let's go back to our worksheet now. Okay, so I've done that example. Now you go ahead and, oh, I like that we're still in pink. Now you try this exercise here. I will work it out and run through the solution with you in just a few moments. Go ahead and pause the video and give this a shot on your own. Boom, and there's the solution. Okay, so let's run through this. We have the function f of x, y equals y over x squared plus y squared. If we set z equal to 0, we get y over x squared plus y squared equals 0. This implies that y equals 0 just because of how fractions work. The numerator has to be 0. Let's note that the origin is outside of the domain. So if y is 0, x cannot be 0. Graphing this, y equals 0 gives me this blue line along the x-axis is where the elevations are 0. Now if z equals 1, we get y over x squared plus y squared equals 1. This implies that x squared plus y squared equals y, implies that x squared plus y squared minus y equals 0. If I complete the square here, I get x squared plus, parentheses, y minus 1/2 squared, quantity squared, equals 1/4. This comes, I'll just add in a quick descriptor here. We always want inside the parentheses, so I had y squared minus y. If I complete the square, I put in parentheses y minus whatever half of the coefficient of y is on the previous line. So it was -1, so we have it as -1/2. And then I close parentheses squared. Now what that did is that added 1/4 to this side when I did that completing the square, so I had to add 1/4 to the other side as well. Let's note if you FOIL this out, you'll get -1/2y and another -1/2y, which is why we need that -1/2 there to get the -y term above. So that's my quick explanation for how we're completing the square. If you want more information, just Google or YouTube completing the square examples, and they will go into much more detail for you. But we want to focus on this contour map here and not go into the details of that algebra right now. So this gives me a circle of radius 1/2, because the square root of 1/4 is 1/2. It shifted up in the y direction by 1/2 due to the -1/2 in the parentheses next to the y. So that gives me this circle here. The center is at 0, 1/2, and it has a radius of 1/2 for a diameter of 1 from the origin up to y equals 1. And this is where my z values are 1. And I'm going to go through this a little bit quicker here. If z equals -1, then we get y over x squared plus y squared equals -1, implying that x squared plus y squared equals -y. We can go ahead and reorganize this and complete the square. We can also think by symmetry of what we just saw above, that we're going to get x squared plus parentheses y plus 1/2, close parentheses squared, equals 1/4. This gives me this green circle here that's shifted down -1/2. So it shifted down to be a circle with the center being 0, -1/2, and having a radius of 1/2 going from the origin down to y equals -1, and from x is -1/2, y is -1/2, to x is +1/2, y is -1/2 as the right edges, right and left extreme edges of this circle. If z equals 1/2, then I get y over x squared plus y squared equals 1/2, which implies that x squared plus y squared equals 2y. We do some rearranging. We get x squared plus parentheses y minus 1, quantity squared equals 1. This gives me a circle of radius 1 that shifted up 1. So we have my dark purple circle here on the graph. Gives me when z equals 1/2. The reason I chose z equal to 1/2 was actually because I'd chosen z equals 2, and you guys didn't see me working this out. When I chose z equals 2, I saw that I was getting a smaller circle than what I had before, which is fine, and I could have drawn it in. I could have gone ahead and put, let's do this sky blue here, that we're going to get an even smaller circle when z equals 2. And so we see that we're getting elevations that are going up the closer to the origin in these tiny circles, and then symmetrically we're going to get elevations that drop way down as we get into these closer and closer circles to the origin that are below the x-axis. And I'm just inferring this from the symmetry of how these solutions are working out. If I do z equals -1/2, again, I'm just doing by symmetry. I didn't do any algebra here. I just knew that it was going to work out the opposite of the previous work. So we should get x squared plus parentheses y plus 1, close parentheses squared equals 1, which gives me a circle shifted down 1 in the y direction with a radius of 1 or a diameter of 2. So we have this pink circle with a center of 0, -1, and a radius of 1. This gives me where z equals -1/2. So we see in general that if we are below the x-axis, that we're getting z values that are flattening out, getting closer and closer to 0 as we have bigger and bigger radiuses with centers on the y-axis lower and lower down. And as we move towards the origin along the y-axis, we get circles that have a z value that are more and more negative. So our elevations are shooting down. We should get a spike as we get closer and closer to the origin. And when we're above the x-axis, when y is positive, we have the opposite thing happening, where our z values are now all positive, but they're flattening out the farther from the origin that we get in these concentric circles. And as we move towards the origin, our z-values are spiking to be larger and larger the closer and closer to the origin that we get. Again, let's go ahead and just throw this into GeoGebra to give us a sense of what this looks like. Close out my previous ones. So f of x comma y equals, get a fraction here, y over x to the second plus y to the second. So we see these concentric circles. It's almost hard for GeoGebra even to get a good idea of what this is looking like. But we get elevations of, oh, I want to move my z. Here we go. This gives us a little bit better picture of what's going on. So if we have that center at 1, 0. Here it's kind of nice with these gray sections to see what's going on there. So if we have x, oh, where are we at? Flip it this way. There we go. So now we have the positive x-axis to the right, the positive y-axis in the upward direction. We see if we're looking at 0, 1, then we should get a circle right here where the elevations are all the same. So all the elevations right here have a z-value of 1/2. And so again, right here at the origin, it looks like we have like this vertical line, but it's actually undefined. We can't have x and y both being 0, but we can get infinitely close. If I zoomed right in, we would actually see that we're not quite touching the z-axis. In fact, the computer breaks down as it tries to get too close to it. But that's the kind of picture that we're getting in this situation. Cool. I love this software. I started playing with it probably a year ago, and I just am amazed at how much more powerful it is than anything else that we've had via calculators or anything before this. So, okay. Let's keep on keeping on. Scrolling down. Section 6.3, graphing a function in 2 variables by hand. So we're not going to get into a ton of detail. What we really want to take is to extrapolate a contour map that we have in the x and y plane and try and draw a picture of what it looks like in 3 dimensions. So I'm going to look at example 6.3.1, use the given contour map below to sketch the graph of the associated functions. So let's just take a look. I'm going to have, we're not labeling all of these. We have z is -8 for this contour line here. It looks like a parabola. We're not giving an x or y scale, so we're just going to assume a 1/1. And so we have a parabola. This parabola here, if I try and draw it, we want a z-value of -8. So let's get a z scale at least on here. -4, -8. Draw in your labels for your x, y, and z. Let's do something other than light blue here, make this a little bit easier to see. So if z is -8, we're going to have a parabola that starts here. If I take a distance of -8 and go straight down from this point, looks like it's about here, that should be that part of the parabola. And I just want to try and get an idea of how this would look from this angled view. And we know it's not going to look exactly the same as how it started because it gets skewed as we tilt the plane back. So it's going to look flatter. We get some shape that looks like this. Now z is -6. Let's do this in a different color. So z is -6 here, except for that's going to happen when y is brought in a little bit, say about here. So I'm going to go down -6 to about here and get my parabola shape in this direction. And I'm going to do this again when z is -4. Let's do red. So this happens, it looks like if this distance is copied, looks like about a third of the way from that -8 spot. So here, and we go down -4 to give us a parabola that looks like it's going to be about here. Then we're just going to keep doing this. Let's jump to the +8 here in a second. So I have +8, and this looks like when y is just over on this side. So I'm going to go all the way up to a +8. And I don't really need to draw in every single one of these. We see that this parabola shape that we're getting is moving upward in the z direction more and more quickly as y goes negative. So we have, like, in this opposite direction, let's do this, I do like that pink. So if I look at this, we're getting this almost parabolic way that our parabolas are going up along this line. If we have this point at 0, 0, when x is 0, y is 0, we get that same parabola shape when and z is 0. So here I'm going to have this. Let me draw my same parabola shape at this angled view, like so. And this is essentially what this is looking like. I can't tell if this is just going to keep going down or if it's going to turn at some point, but from all the information that we have in our contour map, this is all we know, so this is all we're going to draw. I will go ahead and do some parallel lines in this other direction, because we are seeing this kind of shape. It gives us a little bit more description of what's happening. We kind of connect the dots in both directions, so we get this kind of shape. It's like a slide shape, yes? Okay. And that's all we're looking at. We are not looking at grading your ability as an artist, but we are looking for you being able to at least show that you can see what the picture looks like in your head. So do your best to try and get a picture of what this shape looks like on your paper, and then move on to this next one and try on your own to see if you can't graph in 3 dimensions what this contour map is trying to describe. So now you try, go ahead and pause the video, and I will run through the solution here in just a few moments. All right, and here is the solution for this exercise. Let me scroll this up just a hair. All right, exercise 6.3.1, we have this contour map that are these squares that are turned at 45-degree angles. So we get from, again, the x, y directions don't have their scale. We'll assume it's a 1-to-1. That's similar to the z values here. We get a z value of 3 right when x and y are both 0. We get a z value of 2 at the square from 1, 0 to 0, 1 to -1, 0 to 0, -1. And then we get a z value of 1 when we have x from the square from 1, 0 to 0, 1 to -1, 0 to 0, -1, and so on and so forth. The z values keep going down until we get to a z value of -3 when we have from in the square that goes from 6, 0 to 0, 6 to -6, 0 to 0, -6, and back to 6, 0. So I'll start by setting up my x, y, and z axes. Let's actually forgot to label my x and y axes. So here's my x axes, my y axes, my z axes. I go from z is -4 to +4 in the z direction. I started with drawing a blue dot at the point 0, 0, 3. I then actually did when z is 0, because it allows me to get the shape on the x and y axes. So when z is 0, we have the square from 3, 0 to 0, 3 to negative 3, 0 to 0, negative 3 and back to 3, 0. So I draw in those points on my x and y axes, connect the lines, and that gets me a shape to start with. I then see that when z is 1, we get this red that is actually a square, but when it's tilted at this angle, it looks more like a parallelogram. So we have this square that's smaller than the blue square we just drew below and straight up from it. And then we have the green square that again looks like a parallelogram above this, that's smaller again. And so we should get a line that connects from when z is 3 at 0, 0, 3, straight down the corners of these boxes to get me this shape of this pyramid here. So I have these 4 gray lines that trace out the corners of our squares. And then that allows me to quickly draw in the parallelograms that are actually squares for when z equals negative 1, when z equals negative 2, and z equals negative 3. And we see that this 4-sided pyramid is the shape that we should be getting. And this is a little bit skewed. I don't think I did the best job with getting my scales right on the x and y axes, but this is a good approximation of what shape we have. I can... and yeah, we're just going to leave it at that. So let's go ahead and move on to the last page of this lesson, 6.4, functions in 3 variables. Let's start with our definition. Definition 6.4.1, a real-valued function f in 3 variables is a function whose domain is a subset of R3 and whose range is a subset of the set of all real numbers R. Since the totality of the domain and range is 4-dimensional, we cannot view a graph of f in its entirety. However, we may see its level surfaces in 3 dimensions. Analogous to level curves in 2 dimensions, a level surface will show us all points in 3 space that output a given k value in the range of the function. Okay, so we're not going to be able to draw these specifically, but we are going to go ahead and be able to see for a given output what inputs give that output. So in the previous examples and exercises we saw for a given z value, a given output, we could draw the 2-dimensional curve that matches. Let's even scroll up and take a look here. Let's go back a couple of pages. So for a given, if I'm looking at example 6.2.3, for when z is 0, we see that all of the points on this blue line is where that z value is going to be 0. Now if we go down here to this example, let g of x, y, z equal the natural log of 25 minus x squared minus y squared minus z squared, close parentheses, period. Evaluate g of 2 comma negative 2 comma 4 and determine the domain and range of the function. So just starting with some basics here before we get into graphing is g of 2 comma negative 2 comma 4. Come on, pen. Oh, it's just behind and it's processing here. This equals, well, I take the 2, plug it in for x, the negative 2, plug it in for y, and the 4, plug it in for z. So we get the natural log of 25 minus 2 squared minus parentheses negative 2 squared minus 4 squared equals the natural log of 25 minus 4 minus 4 minus 16, which equals natural log of 1 equals 0. So we get an output of 0 when x is 2, y is negative 2, and z is 4. Now this output is in some 4th dimension that we can't really see, so there's no way of describing this normally. I will talk about some ways of thinking about time and how we can work in that manner for how to think about this, but it's still quite difficult, if not impossible, for us to picture in our brain, some image that goes along with this. And that's okay. We can have a function of more than two variables and still make sense of what it means to have an output without necessarily having a picture so much. So we still want the domain and range of this function. Let's note now that the inside of the natural log, which is 25 minus x squared minus y squared minus z squared, that this has to be strictly greater than 0 since the natural log can only take in positive inputs. If we add my x squared, y squared, and z squared to the other side, we get x squared plus y squared plus z squared is less than 25. This shows me that we're in 3 dimensions now, so r squared is less than 25. This is less than 25, so we see that r is between -5 and +5, strictly, no equal signs here. If I were to draw this domain, we have to recognize that we are in 3 dimensions. And so we would get really a sphere I should really be using dotted lines for this. You know what? I'm going to pause the video and draw this a little bit nice. All right, I think that looks a little bit better. So we have a sphere. This has a radius of 5. And so our domain is inside of this. These are the only points in 3 space that are going to give us an output at all. So if I have a point out here when, say, x is 6, y is 5, and z is 1, then we're just not going to get anything out of this function. The outputs are now outputting something in some 4th dimension that we can't see. Now the range, well, the natural log itself can output anything, but we need to be sure that it's actually going to output things that could be all real numbers, right? The natural log, say I want to use different variables than what we're already using. So in our normal one-dimensional input, we see that our natural log could take on any value from -infinity to infinity. Let's note, though, that we're never going to output something like the x squared, y squared, and z squared are all being subtracted from 25. So the least we could subtract from 25 is 0. So we're always going to have that the range, the outputs, let's say g is outputting w's. So let's say g of x, y, z are outputting w values. Then we know that w has to be less than or equal to the natural log of 25 because our inputs x, y, and z are going to shrink that 25 down, and the natural log is going to increase as the inputs increase and decrease as the inputs decrease because of how our natural log function works. So my outputs are less than or equal to the natural log of 25, plain and simple. That is really the range of this function. So I'm going to write this in proper set notation. Say the range of g equals a set of w in the set of real numbers such that w is less than or equal to the natural log of 25. We'll just leave it as an exact value here. All right, last example for, oh wait, no, we have some exercises for you. All right, yeah, you're going to do one of these in just a moment. So, example 6.4.2, describe and graph some level surfaces to the function f of x, y, z equals x squared plus 3y squared plus 5z squared. We already see the graph that I've made in GeoGebra down here, but let's just take a look at how these surfaces are coming about. Note that there's a cutout in this graph, so you can kind of see the inners bits. So say we want omega to equal 0. So that's going to give us that x squared plus 3y squared plus 5z squared equals 0, but this only happens at the origin. So this function will only output 0 at the origin. Okay, what if we want the outputs to equal, say, 1? So let's say w equals 1. Let's note here I'm letting f of x, y, z equal w. So w equals 1, that gives us x squared plus 3y squared plus 5z squared equals 1. I'm going to reorganize this. Let's remember that the equation of an ellipsoid is x squared over a squared plus y squared over b squared plus z squared over c squared equals 1, where a, b, and c are the stretches in the x, y, and z directions. If we think about transformations of functions, this a is actually stretching the x direction by a value of a, the b is stretching the y direction by a value of b, and the c is stretching the z direction by a value of c. Just write that where a, b, and c are the stretches in the x, y, and z directions, respectively. So what we want is to put our equation x squared plus 3y squared plus 5z squared equals 1 into this form. So to do that, I'm just going to bring this 3 down to the bottom as a 1/3. Note that this y squared over 1/3 is the same thing as 3 times y squared. Take it a second, make sure you're okay with that. I'm bringing the 5 down as a 1/5 in the denominator here. So we get a stretch in the y direction of 1/3, the square root of 1/3, because it's b squared. So the stretch in the y direction is b, and the denominator is b squared. So stretch in the y direction is the square root of 1/3. Stretch in the z direction is the square root of 1/5. Now, if we let w equal, let's go with 15. I'm doing that because it's a multiple of 3 and 5 both. Let's change our colors here, yeah? Green. So if w equals 15, we get x squared plus 3y squared plus 5z squared equals 15. I'll divide the 15 over to the other side to start getting it into the form x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. So divide this 15 on both sides. I get x squared over 15 plus y squared over 5 plus z squared over 3 equals 1. So stretch in x is the square root of 15, the stretch in y is the square root of 5, and the stretch in z is the square root of 3. We can see that on this graph here kind of nicely, that in the x direction it's stretched more than it is in the y and the z direction, that it's stretched in the z direction the least of the three different directions here. We see that the center of these ellipses are all the origin. And so to get these different outputs, we have these level surfaces. So for each of these, let's go ahead and pull up the GeoGebra here. I'm going to type in that link real quick. It doesn't work in the software that I'm working with as well as I would like. So KYQ 5UEZY. So this was actually pretty tough for me to do, to get these cutouts, but the idea is all here. Where we got? Okay, so I needed to actually graph the top half and bottom of half of these individually. So I set the z value equal to 1 here, and then, and this, it looks like, sorry, no, I set the w value equal to 1, and then solved for z to get this square root, but when I did so, it ended up being a plus or minus square root when I solved for that z. So I need the top half of the ellipsoid and the bottom half separately. So here these subscripts are telling us what the w value is. So f1 and g1 are the top and bottom halves of the ellipsoid for when w equals 1. When w equals 3, then we have the top half and bottom half here. And when w equals 5, we have the top half and bottom half here. And this gives us our concentric ellipsoids. And I just did this, these restrictions on the x values are to keep it so that I'm not getting this top slice, so that we can see into these shapes and see these concentric shapes here, ellipsoids. So these are giving us the level surfaces for when we're getting our different outputs. This is not the shape. We can see that all of our outputs, I mean, that really the domain of this function is all of R3. So every point in R3 is going to give us some output. And these level surfaces are not the graph of the function. They are just simply the graphs of when the function takes on certain outputs. So we could think of this in a time manner. If x, y, and z were functions of time, we could have a single input of time, and we could see that we're going to get different level surfaces at different times, and those different level surfaces kind of give us different outputs. Now that's not exactly what's going on, but that may be some way of kind of helping us visualize what's going on here. So go ahead and move on to this exercise 6.4.1. And pause the video, give this a shot. So really try and, I mean, you're going to use GeoGebra to graph these level surfaces, but do some of this work by hand, get some of it sketched out on this page, and then come back and take a look at my solution. I'll show you what I've done to hash all of this out. All right, let's wrap this lecture up. Exercise 6.4.1. Describe and graph some level surfaces to the function f of xyz equals x squared minus y squared minus z squared. Let's let f of xyz equal w. If w equals 0, we get x squared minus y squared minus z squared equals 0, which implies that x squared plus z squared equals x squared. This gives us a cone with the axis of symmetry being the x-axis, no shifts or stretches. If w equals 1, we get x squared minus y squared minus z squared equals 1. This is the equation of a hyperboloid of two sheets with the x-axis being the axis of symmetry, no stretches in any direction. And keep in mind here, you might go back and look in Chapter 9, there is a nice sheet page that shows all of the different, or the 6 different basic surfaces that we look at: cones, hyperboloids, parabolic hyperbolas, ellipsoids, blanking on everything now, hold on. We got elliptic paraboloids, hyperboloids of 1 sheet, hyperboloid of 2 sheet. I feel like I'm forgetting one. Was that 6? Cone, ellipsoid, elliptic paraboloid, hyperbolic paraboloid, hyperboloid of 1 sheet, hyperboloid of 2 sheets. That's all of them. Okay, cool. You can look up those general equations so you can kind of reference that as I'm going through this. If w equals 5, we get x squared minus y squared minus z squared equals 5. I divide both sides by 5 to put it in a standard form. This shows that we have a hyperboloid of 2 sheets with the x-axis as the axis of symmetry. There's a stretch in the x, y, and z directions, all by the square root of 5. If we let w equal -1, we get x squared minus y squared minus z squared equals -1. I move the negative to the other side, I get negative x squared plus y squared plus z squared equals 1. This shows a hyperboloid of 1 sheet now, with the x-axis as the axis of symmetry, no stretches. If w equals -5, we get x squared minus y squared minus z squared equals -5. Moving the -5 to the other side, I get negative x squared over 5 plus y squared over 5 plus z squared over 5 equals 1. This gives us a hyperboloid of 1 sheet with the x-axis as the axis of symmetry. The stretch is now equally in the x, y, and z directions, all by the square root of 5. So this should give us some idea, maybe, of what's going on in our head. Let's go ahead and take a look at this in GeoGebra. You can click on the link at the bottom of the page. I already have this open in another window. So I've done it for, I didn't get the w as -5 in here, but sure, let's just do that real quick. -5 equals x to the second minus y to the second minus z to the second. You can throw that in yourself. Gives us this one. I'm going to change the color here. Oh, what's something I haven't used? We have blue, purple, green, pink, yeah? And we can kind of turn these on and off to get our different pictures here. We see the blue one appearing and disappearing as this hyperboloid of 2 sheets. Here's my hyperboloid of 1 sheet. Come on, let's spin this. There we go. So we can see these like concentric hyperboloids that center down to be a cone when the output is 0, which is pretty cool. So yeah, and that shows us, and my computer's freezing, it's not liking how much processing power it's using for all of these. Pretty cool. We're breaking the internet. But that's it. That's us getting an idea of what different 3-dimensional surfaces will get us different outputs for this function in 3 variables. And that's it. That's our lesson for the day. Thank you so much, and we will see you next week.